Okay, so here I have some exponential functions, actually exponential equations here, and I want to solve for x. They're exponential equations because the variable's in the exponent. So 16 is equal to 4 to the x power. Well, what do I have to raise 4 to in order to get 16? Well, since 16 is equal to 4 squared, I could say that x is equal to 2. And that's great. But what about 25 is equal to 3 to the x power? Well, 3 squared is 9. 3 to the third is 27. So some number between 2 and 3? What exactly is it? Well, we can't just guess and check like we did for this. So what we actually need to use is an inverse operation for an exponential. That inverse relationship, that inverse operation for an exponential is called a logarithm. So notice this relationship here. Y is equal to a to the x. So I can rewrite that as y is equal to log base a of x. This is not right. Ignore this. If y is equal to a to the x power, I can isolate that exponent by saying, hey, x is equal to log base a of y. That's what we want. Yes, that is the relationship there. So for example, here, look at what we have. We could do 16 is equal 4 to the x power. So isolate the exponent. X is equal to log base a. Notice base is the same as base. The base of the log is the same as the base of the exponent. That's on purpose. It's the same word. It's going to be the same value. So the exponent x is equal to log base 4 of 16. And we can evaluate this to be 2. Let's rewrite this now. If I want to solve for that exponent, x, I get x is equal to log base 3 of 25. And I can actually use a calculator or something to evaluate this. We'll come back to that in a second, but let's actually evaluate this. Let's rewrite these. So let's think log base 2 of 32. Well, this is going to be the same. If this is x is equal to x, I could rewrite this as 2 to the x power is equal to 32. Well, 2 to the what power is 32? Well, that's 5. 2 to the fifth is 32. Same thing with the second equation. If I can say log base 3 of 1 is equal to x, I can rewrite this as 3 to the x power is equal to 1. Well, 3 to the what power would be 1? Well, 3 to the 0. And actually, anything to the 0 power is 1. So whenever we take a log of 1, we get 0. If you take the log of 1, you will get 0 no matter what the base is, because that's saying 3 to whatever is equal to 1. What about this next one here? We're gonna, if we set this equal to x, we could rewrite this as 4 to the x power is equal to 2. Now this one is tricky because we're going backwards. Well, if we think about it this way, we can actually think about it in 2 different ways. I won't approach the other way right now. There's another way to look at this, and you can actually come back once we've looked at all of the different properties later on and try and reimagine this. But for right now, I could say, well, what's the relationship between 4 and 2? If you realize that 2 is the square root of 4, then 4 to the 1/2 power is equal to 2. Remember, whenever we have fractions as our exponents, we take that root. So 4 to the 1/3 would be the third root of 4. Because this is 4 to the 1/2, we're taking the square root, the second root of 4. And finally here, this one's tricky because it's a fraction, but if we say that this is equal to x, we can rewrite this as 10 to the x power is equal to 1 over 100. Remember your exponent properties. If I have 10 to the x power is equal to 100, it's easy to see that x would be equal to 2. But how did this move to the denominator? How did this become 1 over 100? That exponent must be negative. So we get x is equal to negative 2 because 10 to the negative second power is 1 over 100. All right, we want to evaluate these at the given functions. So if I actually look at this, I get log base 2 of 16. I haven't taught you how to evaluate this in your calculator yet. However, if I ever have the base of the log the same as the base of the exponent, they cancel out to 1. So I could rewrite this as log base 2 of 2 to the 4th. 16 is equal to 2 to the 4th. This right here reduces to 1. So I'm going to get x is equal to 4. Also, probably the way I just went over, we can set this up as an equation. So, So log base 2 of 16, if I rewrite this, I'm going to get, if I say that this is equal to y, I'm going to get 2 to the y power is equal to 16, so y is equal to 4. For this second one here, if I set this equal to y, so I say, all right, log base 16 of 1/4 is equal to y, then I get 2 to the y power, not 2, that's from the previous problem. I'm going to get 16 to the y power is equal to 1/4. Well, how do I get from 16 to 4? Y would be 1/2 because 4 is the square root of 16. But this moves it to the denominator. So we have a negative exponent. Y is equal to negative 1/2. For this third one, I'm going to have log base 10 of 1 over 1,000 is equal to y. So we can say that the base 10, so 10 to the y is equal to 1 over 1,000, just like I had before. 10 to the third would be 1,000, so 10 to the negative third is 1 over 1,000. And finally, for this last one, I can say log base 10 of 10,000 is equal to y. So 10 to the y is equal to 10,000. Might take some guessing and checking there, but that's actually going to be 10 to the 4th is 10,000. So y is equal to 4. So those are our answers there. Notice I didn't do any weird math or anything. This was just rewriting and kind of guessing. Actually, for that first one, I started doing it a different way. I haven't taught you yet that we're going to go over in the future. And there are better ways to evaluate this. But the whole purpose of this exercise is this rewriting, changing these from an exponential form to a logarithmic form. Much in the same way as if I have y is equal to 5x, I can rewrite that as y is equal to well, if I have y is equal to x divided by 5, I can rewrite that as y is equal to 1/5 x, right? If I have y is equal to x divided by 5, that's the same as 1/5 times x. These are reciprocal operations, so I can rewrite them. And that's what we're doing here. Now, a couple special cases. We went over this first one. Whenever we have log base a of 1, that's always going to be 0. No matter what the base is, when we take the log of 1, we're going to get 0. Whenever we take the log of some value that's the same as the base, that's going to be 1. And actually, these are the same here. This ln, that is the natural log. So that only occurs when the base, that's the log for base e. That's the natural base, natural log. So when we take the log of 1, we get 0. When we take the natural log of 1, we get 0. When we take the log with the same base, we get 1. So when we take natural log of e, we get 1. Because here, this is really log base e of e, and those two are the same. So we get 1. Natural logs and logs are the same, but work on rewriting these, and we will start looking more carefully at logs and really getting into the thick of it.